Okay, we are at 16.3 potentials, charge conductors, and equipotential surfaces. We did an experiment Thursday on equipotential surfaces, so this may clear up some of the ideas that you may have confused you during that lab. Let's share the PowerPoint, and there we are. We know that the work is equal to the negative of the change of potential energy. We also know that the potential energy is equal to Q times VB minus VA. Um, and so if we combine those two, we have that the work is equal to the minus Q VB minus VA. Now, if VB and VA are the same at the same potential, then no work is done. This is a conservative force. This is like when it came to gravitational potential energy. If you hold something and just move it from side to side, you're not doing any work in terms of gravitational potential energy. You either have to raise it to give it more potential, or if you lower it, it loses some potential energy. But if you just keep it at the same height, it was mgh, if h stays the same, you have the same potential energy. It's the same here. If VB and VA are at the same potential, then VB minus VA is equal to 0, and you have no change in potential energy, and you've done no work. So notice from the spacing of the positive signs that the surface charge density is non-uniform. I think we've already described how they tend to congregate at points. However, the electric field is the same all around the surface. The electric potential is a constant everywhere on the surface of a charged conductor in equilibrium. Also, the electric potential is constant everywhere inside a conductor and equal to that same value at the surface. So you can see if we move from A to B, we've done no work because it's all on the surface. They're all at the same potential, the same electric potential. Okay, now we're going to define an electron volt. Now, a charge is on an electron or a proton, a single charge is 1.6 times 10 to the minus 19 coulomb. So an electron volt, 1 eV, is equal to 1.6 times 10 to the minus 19 coulomb volts. So, and that's the same as 1.6 times 10 to the minus 19 joules. So 1 eV is equal to 1.6 times 10 to the minus 19 joules. Equipotential surfaces. Now, here are, if we look at a single point charge, a positive charge, we know that the electric field lines radiate outward in every direction from the charge. Now, if we were to draw circles around everywhere where the electric potential is the same, we get the equipotential surfaces. Now, notice that the equipotential surfaces are at right angles to the field lines. There's always a right angle between the little blue dash lines and the radiating electric field lines. And here on B we have a dipole, and you can see how these equipotential lines very near the center line connecting the two charges, they're spaced evenly. That's what you should have gotten this only longer lines when you did your parallel plate or your parallel lines on your equipotential surface experiment. And I think there's even I think there may be a drawing that they ask you to do that's, I think it's similar to this drawing here. So these are the equipotential surfaces. Now, if you look at, I might just draw it for you. Let's see if I can. Let me switch to the iPad. And let's look here on the circle one. If you look at anywhere on here, why won't it? Hold on, it's going to go blank for a minute, I think. Register my pen. Now let's see if it works. At every point here, anywhere you see the blue line and the orange line, you can draw a 90-degree angle. So the equipotential lines are always 90 degrees to the field lines. They're always at right angles. You pick any one you want. You can draw a right angle, or you can draw the little right angle symbol because they're all at right angles to the surface. Let's go back to the PowerPoint of the same one. And there's one more equation to show. V equals KE Q over R. That's the voltage as you radiate out from the positive, the voltage goes lower. You should have seen that on your experiment from last Thursday. As you went away from the positive, your voltage got lower. Okay, I think that does it for this. I'm going to skip the next two slides, the next section on applications. You're welcome to read the applications. I don't see that it does. It's very good. I'm not gonna test you on it. So we're just gonna skip section 16.4 and go straight to capacitors. All right.